Hello and welcome to this video. In this video, we would learn about Huffman encoding. I remember that I had said that I will talk about general search tree, but certain things are pending in ordinary binary search trees. One of those is Huffman encoding. Then we have suffix trees and some other trees we will study, and then we will move on to general search trees. So, what is Huffman encoding? Now, suppose we have an alphabet of n symbols and we construct a long message from this alphabet. Now, our objective would be to minimize the length of this alphabet. So suppose we have A, B, C, D, and the codes for those alphabets are 0, 1, 0, 1, 0, 0, 0, 0, 0, and 1, 1, 1. These are the codes for symbols A, B, C, D. Now, if we encode A, B, A, C, C, D, A, then it would be a 21-bit length string. Because why we are converting to 0 and 1 is simply because everything in the end has to be converted to 0 and 1, that is the voltage levels. Now, the problem with this encoding is that it is inefficient, okay, because 3 bits were used for each symbol. What Since these are 4 symbols, we can probably do away with 2 bits. So we take 2-bit representation for ABCD 0, 0, 0, 1, 1, 0, and 1, 1. In this case, we will have 14 bits. But can we do better? The logic to do better comes from the fact that in this string, A has come 3 times, C has come twice, B and D have come once. So if we take smaller symbol for a smaller bit length for A, that is the high frequency items, and larger sequence for less frequent symbols, then probably we can do it better. So one such mechanism is 0, 1, 1, 0, 0 for A, 1, 1, 0 for B, 1, 0 for C, and 1, 1, 1 for D. Now if you encode, it requires only 13 hits, 13 bits, not hits. So in very long messages containing symbols that appear very infrequently, the savings are substantial. Ordinarily, codes are not constructed on the basis of the frequency of characters within a single message alone, but on the basis of their frequency within a whole set of message. The same code set is then used for each message. Now, how do we construct such an encoding table? So let's look at this tree. Here we have B with frequency 1 and D with frequency 2. So if we combine BD and treat them as one symbol, then BD comes twice and C comes twice. And then we combine again CBD, actually, not BCD, CBD. It will have frequency of 4 and A will have frequency of 3. So combination would be having a frequency of 7. Sorry, not frequency, length of 7. Or yeah. So how do we do it? So first we take B and D, and the last bit we have to differentiate. So we take 0 for B and 1 for D. Now we combine these two into single symbol BD, as I have shown. So whose code represents the knowledge that the symbol is either B or D. The frequency of occurrence of this new symbol is the sum of the frequencies of two constituent symbols. So the frequency is BD is 2. So yes, I was right that it is frequency, not the length. Now we have 3 symbols, A with frequency 3, C with frequency 2, and BD with 2. Again, we choose the 2 symbols with smallest frequency, C and BD. The last bit of their code again differentiates one from the other. 0 for C and 1 for BD. The 2 symbols are then combined into a single symbol CBD with frequency 4. Now there are only 2 symbols remaining, A and CBD. These are combined into a single symbol ABCD. The last bit of the codes for A and CBD differentiate from one from another. There are lots of typing mistakes. 0 for A and 1 for CBD. So see how it how do we make it? So B and D we choose last bit is 0 and 1, and then we pick C. So for C the last bit is 0, and for B and D we put 1. Then for B, C, D and A combination we put 0 for A and 1, 1, 1 for B, C, D. So that's how we construct. Now this tree which I have shown is called a Huffman tree, and we can use it to find the code for our symbols. So we will do a C implementation for this using minheap. So this is the source code of minheap, the Huffman encoding scheme. So we go through this very quickly because I have already explained minheap. So first is we force a height of 100 nodes. Okay, that is the max we can have. Now minheap node, as you know, will contain the data, that is the symbol, the frequency, and two children, left and right. And this minheap will have size, capacity, and array of midheap node pointers. So this is a node and this is the minheap. So minheap contains array of pointers, node pointers. Now how do you create a new node? You receive data and frequency, you allocate memory for a node, and then you set left and right child to null, and data is set to data, frequency is set to frequency, and you return temp. That's how we create a new node. Now how do we create a min heap? This is creating a new min heap. We allocate a new min heap and set its size to 0 and capacity to capacity. Capacity is passed here, and for the array you do allocation for array with capacity. A swap min-heap node. This is simple swapping function. You swap two min-heap nodes A and B. Now this is min-heapify. I will not explain this function here. If you want, you can go and watch my video on min-heaps and max-heaps. Both you can watch. This tells us, this function tells us if the size of min-heap is 1. This is the function to extract the minimum of a heap. So minimum is always the 0th element. Okay. In a minheap, the topmost, the root node would be the minimum node. And then you decrease the size, and 0th element is now replaced by the last element. And then you, after the decrement of size, you min-heapify this again. To insert a node on min-heap, we increase the size. We take the last node of the size and then we insert on that node, and that's how you insert it. I will again not go into details of min-heap because that is already covered. Now build min-heap is there, where you take a min-heap and you min-heapify this fundamentally. This prints an integer array of length n. This tells if a node of min-heap is a leaf node or not. And this creates and builds a min-heap. So you call the create min-heap function, and for number of nodes you allocate those many nodes. Note that you will receive data, frequency, and size. So you supply the data and frequency here, and for the size number of elements you create new nodes and you set the size of min-heap, and then you call the min-heap function on that. So essentially there is an array of node pointers in an array which we are adjusting to create our min-heap. And then we have build Huffman tree. So it receives the data, frequency, and size. So we declare three nodes, left, right, and top, and we call create and build min-heap. We supply data, frequency, and size. So this function we just saw is used to create the min-heap. And if size of min-heap is not 1, okay, then we extract the left subtrees min-heap and right subtrees min-heap, and then we create a new node. We give it dollar and we supply the frequency of left and right. We add the frequency, and top left becomes left and top right becomes right, and then we insert on the mini the top element. So now we can see how the node is constructed. That's the logic we had just covered in the PDF presentation. So that's how you create it, and the remaining node will be the root node and the tree is complete. And this is simple function to print the code, and then we have Huffman codes here, which basically builds Huffman tree. Now say we have six letters A, B, C, D, E, and F in the array, and the frequencies are 59, 12, 13, 16. First we should try with equal frequency. Let's say equal frequency 9, 9, 9, 3, 4, 5, 6. So we save this and we build it, and then we run this. So see, even with the same frequency, these codes are like what we have practiced, even with the same frequency. Now, if you want, you can make this frequency 20 to see how this changes. So it does not change anything. Let's give it frequency of 15. A and C have higher frequency. So you see what, okay, so I said nothing changed because I did not compile. Now you see, once A receives a different frequency of 20, A is now 11, A is no longer 0. And C becomes 0 here, C was 111. So because of the order of insertion that happens, certain elements get smaller codes. Now we made C 11. So it remains similar. Now let's say we make B 100. So you'll see B will be a smaller one this time. So now B is 1. So depending on the order and frequency, the Huffman code will change. So this is the entire example of Huffman encoding. As an exercise, I will implore you to encode a string. You take a string, you have got the codes here. Now you take a string input and you can encode it. You get the bit string and then you decode that string to retrieve the original symbols. You can use the codes to decode it. So that's an exercise for you. And if you need help related to that exercise, send me a message in comment box and I will uh, probably create another video on how to decode Huffman encoded bit string. So with this I come to the end of this video. In the next video, I will most probably deal with suffix trees or maybe tournament trees. I don't know. So one of these will be covered in the next video, and then we'll see where we can go from there. So we have two trees in picture right now. One is tournament trees, another is suffix tree. Suffix tree is very interesting, so I think I will cover that first, and then we'll see. So thanks a lot for watching. I hope that you have found this video useful and informative. Thanks again for watching. Happy programming.